Hi, my name is Jean-Philippe Bossuat, and I will be presenting my solution to the track 1 of the iDash 2024 challenge. This year's challenge was to securely outsource the classification of encrypted protein sequences among 25 possible classes. Each protein sequence is composed of 50 amino acids, and there are 24 possible different amino acids. In total, we had 100 samples to classify. To perform this classification, a custom and pre-trained model was given to us. This is a change with respect to previous years because we usually had to also design and train our own models. So this year's challenge was solely to write an FHE circuit that best approximates the functionality of the given model. The provided model is composed of 4 main steps: an embedding layer, a transformer, a neural network, and a classifier, each presenting their own challenges. I will now give some more details on how each of these layers were implemented under encryption. My approach to the challenge can be divided into 3 steps, each with their own difficulties. The first one was to reverse engineer the model and translate it into a pure Go implementation. This task wasn't as easy as expected, mostly because it was not always obvious what the scalar layers were doing under the hood, but also because extracting test vector in order to ease the debugging for each intermediate step when running a graph compile model is not straightforward. The second step was to design an FHE circuit that approximates as best as possible the ideal circuit. The main challenges of this step were the non-linear operation used in the softmax normalization and activations. Finally, the last step was to implement the encrypted circuit based on the previous steps, for which I will now give more details. Before going into those details, a few words about the data packing. I choose to go for a row-encoded approach, where the matrices are flattened into vectors by concatenating their rows. Other approaches are possible, but this one was the one that overall provided the best performance for my solution. Row flattened matrices will result into large vectors, and with 100 samples, this amounts to more than 1 million of encrypted values to handle. To avoid a memory blow-up, notably because of the number of keys and all the plaintext matrices of the weights, I ended up loading them on the fly. This is slower than storing everything in memory, but it saves a lot of memory and allows to run the solution on less than 50 GB of RAM. The first layer, the embedding layer, was the first non-trivial challenge, especially because it turns out that its precision has close to 1:1 correlation with the output precision. So it has to be accurate. What the embedding layer does is map a vector to a matrix via a lookup table. This operation can be expressed as applying a column-wise function on a matrix that is the concatenation of copies of the input vector. The embedding layer can therefore be reduced to finding a way to evaluate a high-precision function that maps an integer to a vector of reals. The issue is that direct approximation for an error of 10 to the minus 4, which is more or less the minimum required to have a reasonable output precision, requires a degree in the thousands. This is doable but highly inefficient. But there is a workaround. We know that the values of the input vector are discrete, since they correspond to the 24 possible amino acids. So we actually do not need to approximate the function over the entire domain, only where the value could fall. By using the multi-interval min-max approximation and carefully choosing the interval, it is possible to reduce the degree to only 63, while also having a polynomial with small coefficients. Here we can see an example of why the multi-interval is much better than direct approximation for this case. The graph shows parts of the first function, among 128 of them, where the blue is the ideal function, in green the multi-interval, and in red the Chebyshev approximation of the same degree, 63. The only issue with this approach is that finding these minimax polynomials was very time-consuming, and I had to do it for 128 of them. The next layer is the transformer, which presents several challenges. Luckily, most of it is straightforward, in principle, as a lot of it can be expressed as public linear transformation over encrypted vectors. Regarding the ciphertext matrix multiplication, I choose to use Jiang and Al approach, as it is one that preserves the output format, is efficient, and I had previous experience using it and implementing it. The softmax is the real challenge of the transformer. This is a large enough challenge that there are entire papers dedicated to it. Being alone, my resources were constrained, so I went for a probably not the most efficient way, but I knew it would be simple and stable. This approach is to normalize the value. Because if we can ensure that the max of the vector is 0 and that there is at least one value that is 0, then the exponential as well as the inverse are easy and numerically stable. Computing the max of the vector can be done by a series of comparisons and hormetic selection, which is something that we know how to do well with FHE. However, I quickly realized that it wouldn't be usable as is. I haven't talked about the parameters yet, but what I can say is that in my solution, 34 ciphertexts are needed to pack the 100 samples. So, if we have an input array of size 50, 7 comparisons are needed to find its max. And if we are optimistic with with one bootstrapping per comparison, then that would mean 238 bootstrappings. If we take about 15 seconds per bootstrapping, we are already looking at close to 1 hour dedicated to the softmax, which was the time limit fixed by the iDash team. So something had to be done about it. The solution I came with was to observe that while computing the max of the vector, part of the vector becomes irrelevant, since after each iteration, the size of the number of slots that need to be pairwise compared is reduced by a factor of 2. This free space can be used to merge two ciphertexts every time at least half of the vector gets liberated. This enabled to reduce the number of bootstrapping to only 34 by shaving the log factor. The same technique is applied for every operation that only operates on a single value among the entire vector. For example, when computing the denominator of the softmax. Instead of doing for each ciphertext, the values are first extracted and packed all together into a done ciphertext. The inverse is evaluated and then they are extracted. Of course, doing so costs additional levels, but overall the gain is well worth it. The neural network is very standard and was straightforward to implement, well, after having implemented the transformer. All linear operations were already defined and it remained to solve the normalization and activation. Regarding the normalization, statistics collected on the intermediate values by fuzzy testing the network showed that their range was consistently far enough from 0 to solely rely on direct polynomial approximation instead of having to use Newton's iterations. In fact, testing has shown that this step was highly resilient to errors, and also so that only a low-degree approximation was sufficient to not degrade the precision. However, this was not the case for ReLU. I hope that would be able to replace it with a smooth function like GLU or CLU, but it turns out that this was not possible. All my stats showed that this step was very sensitive, similar to the embedding layer, and that only a high precision ReLU would not impact the precision too much. Finally, we have a classifier, on which there isn't much to say, as it does not use anything new. Maybe one thing. One might have saw that along with many of the previous steps, often multiple linear operations are chained and that on paper they could be merged as a single one. Unfortunately, and I tried it, in practice this is not always beneficial because it will result in a very costly linear transformation, so much longer to encode, much larger in memory and needing more keys. So it's often better to trade additional level and only have to evaluate sparse linear transformation. And this is very similar to what is done in the DFT matrix or the bootstrapping. And now we have numbers. So regarding the parameters, I use two of them. One for the main circuit, which uses the conjugate inverse CKKS that enables to pack n reals instead of n/2 complex, and one for the bootstrapping over the complex this time. Since we can pack 2 real ciphertexts into a complex one, this enables to make use of the full throughput of the bootstrapping and reduce the number of calls by a factor of 2. You might see that the number of consumable levels of the circuit parameters is one higher than what is output by the bootstrapping parameters. This is because the ciphertexts are encrypted at the 13th level, but they are only pushed back at the 12th level. It turns out that 12th level was, for this circuit, the optimal value to minimize the number of bootstrapping calls, and the 13th level were only needed at the very beginning for the embedding layer. I submitted two solutions, one with high accuracy and one with a lower accuracy. The main difference between the two are in the nonlinear operation, where less precise polynomial approximation are used, enabling to save up to 18 bootstrapping in total. The implementation is generic and modular, meaning it can be reused to implement any model that uses the same operations. The backend uses my fork of the version 5.0.2 of the Latigo library. This is a version that differs quite a lot from the original one with over 30,000 lines changed. It contains many new quality of life features and protocols. If you are a Latigo user, I encourage you to take a look. There is a detailed changelog. Both the library and the implementation of the solution are public. Before finishing this presentation, I have a small anecdote. I've been working on and with FHE for the past 5 years, and this is something that hadn't happened to me yet. So it was the last week before the deadline, everything was going well, I was able to put everything together and start testing the solution end-to-end. Until I started getting rare and random ciphertext corruptions. When printing intermediate results, some of the ciphertext, not all of them but few of them, would decrypt to garbage. This really scared me because it was something that could happen anywhere, anytime, and was very hard to reproduce, only once every hour or so. I was unable to find the root cause before the deadline, so I sent the solution, finger crossed, along with a memo to the evaluation team, telling them I would keep them updated about the bug hunt. A few days later, I got an answer from the evaluation team asking me if results in the order of 10 to the 9 were expected. Clearly not. And this was very bad news. I got a new message a few days after telling me that they actually had mixed up some results and that these were not mine. And well, you can imagine the relief. Eventually, I was able to roll out overflow and race conditions and many other possible causes. And there is only one remaining cause that remains, which is a faulty CPU. I'm not sure, but this hypothesis is reinforced by the fact that I was able to trigger faults by using a stress program, and that nobody around me with whom I had shared the code, and also a small script that is able to reproduce this bug every 10 minutes on my desktop, was able to see it. Before I end, I would like to thank Serong and Intac, who proposed and provided the help to implement the level-aware key switching in my fork, in the hope that it would help to speed up the solution. Unfortunately, the code wasn't ready on time and could not be included in the solution that was submitted, but it is now part of the library and of the public solution. I also want to thank them for the discussion we had on how to possibly improve the solution and their help when trying to figure out where the bug I talked about previously could come from. And to finish my 2 cents on this year's challenge, usually teams would have to both design, train, and implement the model to solve a specific problem. This would always result in a very lightweight model specialist for the solution that were very easy to implement under encryption. As such, much more time was dedicated to the design and training of the model than its FHE implementation, making it more a competition about who was able to find the best plaintext model than an FHE-focused competition. So I'm happy that this year's challenge was a drastic change from the previous years in trying to solve that. I think it was the first time that the model architecture was imposed along with its weights, making it a pure FHE challenge. However, I also think that being the first challenge of this kind, the bar was probably a bit too high with respect to the effort needed from the previous years.